Okay. So we have three theorems lectured for section 5.2. So the first one is about the kernel and the range and their dimensions related to the dimension of the domain. Okay. So T is the linear transformation which has a finite dimensional domain. But the codomain W can be finite dimensional or infinite dimensional, so that there is no restriction for the codomain. Okay? So can be finite or infinite. Dimension. Okay, so for W there is no restriction, but for the domain V, there is a restriction that V has to be finite dimension. Okay, and then the dimension of the kernel of this linear transformation plus the dimension of the range of T is equal to the dimension of the domain. Okay. So we have shown in theorem 1.2.14 that the dimension of the range, of linear transformation on a finite dimension vector space less than equal to the dimension of this. Okay, so we have shown in theorem 5.2.14 last week. Okay, and then we let m equal to, because we already said that the dimension 3 is finite dimension. So you can see the dimension of range is also finite and related called m. All right, since a kernel of T is the subspace of V, all right? So okay, the dimension of kernel of T is also less than equal to the dimension of V. Now, relate U1, U2 up to UK be a basis for kernel of T. We also let top 1 up to Wm be a basis for the image of the range of T. Remember, kernel of T is a subspace of T, and the range of T is a subspace of the codomain. Okay. So, any questions? No? I have to say that the theorem 5.2.14 is very important because the range of P is subspace of W. W can be found out only many dimensions. So, so if we don't know anything, then the range as a subspace, the dimension of the range may be finite dimension or infinite dimension. Okay. But in theorem 5.2.14, if the domain of the linear transformation if V is finite dimensional, then we have shown that the dimension of the range of P is finite. It's fine. Okay. Now, since each Wi in the basis vector, okay, is in the range of P, so there exists Vi in the domain such that P Vi is equal to Wi. Okay, for all I from 1 to n. Alright, so we will claim is that we put them together, right? So we have vectors, right? They are basis vectors for kernel G, and we also have V1, V2 up to Vm. So we claim this set is a basis for V. Right? So we want to prove that. So if this is true, then this is K, this is M. So K plus M equal to the dimension. Alright, so first of all, we have to show that this set spans the whole domain. Okay. So we let V in the domain. Right? So then PV is in the range. And then we can write PV to be beta 1 of 1 plus beta 2 to 2 plus beta m to m. Okay? Because the one of the WM is a basis for the range of T. So we can write this one. Alright, so this implies that T and this is, and we know double I is T of Vi, that is the one is T V1 plus beta 2 T V2 plus beta M T Vm. Right? So that's by substitution here. And now, by linearity of T. So this is T, beta 1, T1 plus beta 2, V2 plus beta plus beta M, Vm. Okay? So by the linearity of T. So now TV is equal to T of this linear combination. So they have the same value. So this implies that TV minus this linear combination is equal to 0 of W. Okay? So this is your vector. So that means that this difference is in the kernel of P. So this means that 3 minus theta 1 is in the kernel of P. So now V minus, so this is in the kernel of P. And so it can be expressed as a linear combination of the basis vectors for kernel G. So this is alpha 1, U1 plus alpha 2, plus alpha k, UK. And so finally, we can express V as linear combination of UI and V rejects. Alright, so any vector in the domain can be expressed as a linear combination of vectors in this set. So this is implies that V is in the span of the set. Okay, so we prove that V is contained here. But of course, we know the span of the set is the subspace of V, because U1, U2 up to UK are in V, V1, V2 up to Vm are in V. So their span is a subspace of V. So V is the span of U1, etc., UK, U1, etc., Vm. Right? So this is the first thing. So we know that V is the span of this set. Alright, so the rest of the thing is to prove that this is a linearly independent set. So now consider an arbitrary linear relation alpha 1 U1 plus plus alpha k UK plus beta 1 V1 plus plus beta m Vm equal to 0. Right? So consider a linear relation on the set. Alright, so we consider a linear relation in the set here. Now we are going to show that all the coefficients are zeros. Okay, this is our purpose. So now we are applying P, okay, on both sides. Alright, so we are applying P on both sides. And because P is linear, right? So we have alpha 1 P U1 plus plus alpha k T UK plus beta 1 T V1 plus delta plus beta M T Vm equal to T 0 V, and this is the zero vector of the codomain. Okay, we have that. Now, because U1 UK, they are in the kernel P, so this is 0. Okay, so they are all zeros. Right, because U1, U2, they are in the kernel P, so their images are zero vector. So this is 0, and so this is implies that beta 1, and this is W1 here, right? W1 plus theta plus beta M Wm equal to the 0. But W1 up to Wm, they form a basis, right? So they are linearly independent. So this implies B1 equal to M. It's a linearly independent set. Okay, so now we prove the coefficient beta 1 up to beta M to be 0. Alright, so now go back to our linear relation. We already showed beta 1 up to beta M, they are the zeros, right? So they are 0. So now we have alpha 1, U1, then plus alpha k, UK, it's the 0 vector. And again, alpha 1 equal to alpha k equal to 0, since U1, and the third, UK, this set is a basis for the kernel, so it's a linearly independent set. Three. Okay, so you see that now again alpha 1 up to alpha k, they are all zeros. So we now show that all the coefficients are zeros. So the conclusion is that U1 up to UK, V1 up to Vm is linearly independent. Okay, so now this set is linearly independent, and this set is span the vector space V. So that this set is a basis. U1 up to UK, V1 up to Vm is a basis for V, and then dimension of V is equal to K plus M. But K is the dimension of the kernel of T, and the M is the dimension of the range of T. Okay, so we have proved the theorem. Questions? Okay. Alright, so no question. And move on to 5.2.18 is called the rank nullity theorem. For matrices. I forgot to name the previous theorem. The previous theorem is the rank nullity theorem for linear transformations. Okay, so this is for matrices. Alright, so for M times N matrix A, the rank of A plus the nullity of A is equal to N. N is the number of columns, okay? Number of columns of the matrix A. Before to give a proof, let me make two remarks. Remember, the rank of a matrix is the number, by definition, is the number of pivots. Okay. Okay? It's the number of pivots. Okay? And second, the nullity of A is the dimension of the null space of A. Okay? So nullity is the dimension of the null space of A. Any question about the definition of rank A and nullity of A? And we also show so this is equal to okay, no problem, right? Okay, so now I will give a proof. The matrix A, okay, this level is average. A linear transformation P from n dimension P space to m dimension, and for every V here goes to every or okay, so that so by metric multiplication, so the matrix, the M times n matrix A establish a linear transformation like this one. Okay, and so the kernel of, as we know, the kernel of P is actually the null space of A, right? We know that from chapter 2. And the range of this linear transform is the column space of A. Any question? I suppose we all familiar with matrices. Okay, so we know the null space of matrix, and we know the column space of it. So the range is the column space. Okay? Okay, good. Now, so we just proved the theorem, the rank nullity theorem for linear transformation. So by and of course V is our domain of P, it's Rn. Right, so now by theorem 5.2.17, the previous theorem, we have dimension of kernel of T plus dimension of the range of T equal to the dimension of V. So this dimension V is N, and so this is N already here. Okay, and now by definition, nullity is just the dimension of the kernel. So now here dimension of kernel of T is the dimension of null space of A. So it's the nullity of A. Okay? So the first term is just our nullity of A. Now how about the dimension of the column space? Well, we have a theorem now by theorem 5.2.13, the pivot columns of A form a basis for the column space of A. Remember that, right? So that dimension of the column space of A is equal to the number of pivots in A. Because each pivot has a pivot column, right? So that the number of pivot columns is the same as the number of pivots. Okay? And so this is the rank of A. So we know the dimension of kernel T it's just the nullity of A. And the dimension of the column space of A is just the rank of A. So that the nullity of A plus the rank of A is equal to the n, and we have done. So this is just a direct application of theorem Python 2.7, 17, I'm sorry. Okay? But you have to know the relationship between the matrix A and the linear transform T is established. Okay, the last theorem for section 5.2. The row space and the column space of a matrix is the same, have the same dimension. And that dimension of the row space of A equal to the dimension of the column space of A. And in many textbooks of linear algebra, the dimension of the row space of A is called the row rank. Of A. And the dimension of column space is defined to be the column rank of A. Okay. So the theorem established that the row rank of A and the column rank of A are the same. Now, how do we connect row space with column space? How do we do that? We have to find a mechanism, right, to connect them together. Otherwise, row space are row vectors, column space are column vectors, right? So you have to find something connecting. And the connection will go back to chapter number 1. Okay, so chapter number 1 always our basic. Alright, so the chapter number 1, so you have to remember. So let U be the reduced row echelon form of A. Right? So now since A is row equivalent to U, right? Row equivalent to U. The row space of A is equal to the row space of U by early theorem. I think it's a theorem where in section number 1. Let me come up with that. Where is it? Okay, so it's theorem 5.1.9. Okay, so this theorem says that if two matrices are row equivalent to each other, then they have the same row space. So they have the same row space. Okay. And note that the typical structure of a matrix in reduced echelon form would be like something so you see, all non-zero rows has a leading one, right? Every non-zero row, otherwise it's just zero rows, okay? So every non-zero row is a leading one. And the leading one will be in different columns, right? That is the very distinct features of a matrix in reduced echelon form. So, so the non-zero rows. So the row space of U is spanned by all non-zero rows. Of course, that is the definition of row space, right? And they are linearly independent, of course, because the leading one are in different locations. Right? So the non-zero rows of U form a basis for the row space of U. Okay? Okay, so they must form a row base. Okay, so the dimension of A of the row space of A is equal to the dimension of the row space of U, and the dimension of the row space U is equal to the number of pivots in A, because every pivot has a corresponding non-zero rows in the reduced row echelon form. Okay, and the number of pivots in A, as we have shown, is equal to the dimension of the column space. Okay. Right? Again, by theorem 5.2.13, and we have done. And then so we now know the connection between row space and the column space will be the reduced row echelon form. Okay? And this form is obtained by applying Gauss-Jordan elimination. So that is the basic, and we all know starting from the beginning of this semester. Questions? Okay, so we'll go forward to the next section about coordinate system. Okay, so we know given a basis, we can construct coordinate vector for such a basis. So let V be an n-dimensional vector space. Can be very general, but just one-dimensional. For example, the vector space of all polynomials of degree less than or equal to n, and it will be a plus one dimension vector space. Okay. Also, if you are considering nth order differential equation. Let me say nth order linear differential equation with initial conditions. All right, with initial conditions. Then you must have n initial conditions, right? Then the solution space, all possible solutions will be n-dimensional vector space of functions. I think you all know at this moment, right? Because you took the different equation last semester, right? Is that correct? Really, right? Last semester, not this semester. So you should know that. Yeah, I'm very happy you know this fact. So I think you already know that, right? If you are considering a linear differential, ordinary differential equation with initial conditions, and you will have n initial conditions at a certain initial time. Usually the time is 0. Then the solution space will be an n-dimensional vector space of functions. Especially if the coefficients are constant, you will have exponential functions, right? As a basis. If some characteristic polynomial has distinct root. I'm not saying martial language, right? I'm saying English. Anyway, so you should know that. So that will be an n-dimensional vector. So it can be very, very general. It can be function space, polynomial, and anything. Okay? So that will be an n-dimensional vector space. And the let V equal to V1, V2 up to Vn. Okay? Be an ordered basis for V. Now, for each vector in the vector space, there exists a unique representation for X as a linear combination of basis vectors B. Okay, so X can be written as our V1 plus our V2, V2 plus theta plus alpha n Vn. Okay, and we call this column vector n as the coordinate vector of X relative to the basis B, the ordered basis. Alright, so even though V is very general, can be vector space of functions, but if we construct, if we are fixed a basis and construct coordinate vector for each vector in the vector space, then we will use the vectors in n-dimensional Euclidean space. We are familiar with those vectors as a tool to study the property of the original vector space. Okay, so that is the importance of coordinate system. Because we will have a standard way to represent every vectors in a general n-dimensional vector space. Okay, and so we can apply a lot of knowledge on matrices, on column vectors, okay, to study a very general vector space. We will encounter in mathematics, engineering, and economics, finance, a lot of things, or social problems. Okay, because we will consider coordinate vectors relative to different bases, because we will study, in many situations, we will study different bases for the same vector space. And for different bases, we will have different coordinate vectors. We will have. Right. So that means that for each basis, we establish a coordinate system. With different bases, we will establish another different coordinate system. So we have a lot of coordinate systems. So we will see the relationship between different coordinate systems. Okay? And we'll find that we will have merit. We will have if we can choose a very unique coordinate system. If we can, we will see how and what of the unique coordinate system, such that the study of vector space and the linear transformation will be very, very simple. Okay? Alright, so that will be the subject of this section and the preparation for the next chapter about eigensystems. So now, we go start. This column vectors is also called so we give a name, also called the B coordinate. The B coordinate. And sometimes we omit the vector of x. Okay? To indicate that the coordinate vector is dependent on the basis we choose. Okay? The way we choose. Right, so before we go further, let's take a break up to 11 o'clock. Okay, let's move on. Okay, so we first of all we have a basis B consists of n vectors because B is n-dimensional. And then we establish coordinate vector vector to the order basically, so we call this coordinate vector as B coordinate. And then we may consider another order basis C consists of n vectors u1, u2 up to un. Alright, and so we would like to know the relation between B coordinate and C coordinate. So we want to know their relationship. Right, and first of all, we recall taking coordinate vector. You know that it's a function from the n-dimensional vector space B to the n-dimensional Euclidean space Rn. And so we know that this is right. So this function is an isomorphism by theorem 5.0.3+4. Right? An isomorphism means a bijective linear transformation from a vector space to another vector space. Right, so now with B coordinate of alpha 1 over to up to alpha n. So we have we can reconstruct the vector x by the components of the B coordinate. So that would be alpha 1, v1 plus alpha 2, v2 plus alpha n, vn. So from time to time, we will write as the sum here. Right? And by now by applying the isomorphism, right, which is to take C coordinate, right, on both sides, right. So we take on both sides. We have x c is equal to summation I from 1 to n alpha I v I c. Okay, so we take this isomorphism, the bracket sub c on both sides, and because the bracket sub c is linear, right? So this is come to alpha I C here. Any question? So this is the coordinate vector in Rn, and these are also coordinate vector in Rn. So that the coordinate C V1 C V2 C Bn C. Right, so we put the linear coming into a matrix multiplication. And what is that? This one is just the free coordinate. So that this is 1 C equals beta Bn C and okay. So now we immediately find a way. If we know to change the B coordinate to C coordinate by matrix multiplication. This is a matrix. Okay. So this one is n plus 1. This is n plus n. This is n plus 1. So this is a matrix. And this matrix will be called the transition matrix from B to C, right? So it's from basis from B coordinate to C coordinate. From where is this construction? It's called the transition matrix. Okay? From the B coordinate system to the C coordinate system. Okay. And from here, you know how to construct the transition matrix. The construction is that you take the vectors in the B basis. Right? Take the vectors in the B basis and then take the C coordinate for each vectors in the B basis. Okay. And form a matrix. Then this matrix will be the transition matrix. So it's quite natural, right? Any questions? Okay, so now we can state the first theorem for this section. I will call it as the change of coordinate system. So now, given to order the basis, B and the C, for an n-dimensional vector space with the B coordinate and the C coordinate of a vector in the vector space are related by x c equal to the matrix, the transit matrix from B to C multiplied with the B coordinate. What do you got? It's equal to n times n transition matrix. Okay, so we summarize into the theorem like this one. Alright, so the remark. The change, okay, from the B coordinate system to the C coordinate system. That we call B to C. Okay? It's an isomorphism. From Rn to Rn. Okay, so the notation for the change from the B coordinate system to the C coordinate is from B to C. So B to C is the change. And this change is an isomorphism, means that it's a bijective linear transformation. Actually, it's a bijective linear operator because the codomain and the domain are the same. They are all Rn. Okay, so let me show it. Right, so this one, taking B coordinate, is an isomorphism. And C also is an isomorphism. Okay, both by theorem 5.2.3+4. Okay, so now the inverse of the isomorphism is also an isomorphism, right? Because isomorphism has symmetric property, so that the inverse, which is Rn goes to V. It's isomorphism. Symmetry of isomorphism. Right? And then now we show that B to C actually is equal to the composition of a linear transformation, this linear transformation and this linear transformation. Okay. So first of all, well, we have B coordinate. Okay, we have B coordinate. We go back to X. All right. So this is go to X by using the component of the B coordinate and the vectors in the basis B to form linear combination and back to X. And then from X we take the C coordinate. Alright? So that things operate on okay. So we operate on the change of B coordinate, right? So we change the B coordinate into C coordinate. Why? So what is that? Because operate on okay, so that is C. Okay. We operate on X, and this is just alright, so the composition, so you can see the composition on the B coordinate will give us the C coordinate. So we have this one. So as a composition of two isomorphism, B to C is an isomorphism too. By the transitivity of isomorphism. Okay, because we show isomorphism is an equivalent relation, means that it is reflexive, it is symmetric, it is transitive. So the composition of two isomorphisms is also an isomorphism. So that we know the change, right, from the basis. Okay. Maybe I put two remarks. And the second remark, the matrix representation of B to C is just the matrix is just the transition matrix. we know that anyway, B to C, or you can write the same, right? And which is just V1, C. Okay. Okay, so this gives us that the change of frequency from the frequency system to the sequence is also an isomorphic, right? From R to R. Okay, now the next question, because we have B to C, so the next question. One is C to B. Because we know B to C, but what is C to B? Alright, so think C to B will transform C coordinate to B coordinate, right? Just by its definition. So this one. And we know B to C is what? Okay, so for there, you see that because it's a measure representation of the, okay, maybe I would say, so a consequence, I forgot the consequence, is that it's invertible. Because in chapter 2, we have to show that if we have a bijective linear transformations, then this is invertible. But actually, I also proved that in theorem 5.2.8. Maybe I will say my theorem 5.2.8. So that the matrix is invertible. No. It's different. It must be in chapter 2. I forgot the theorem. So you can go back to check. So maybe I will say that. Okay, so that they are all invertible matrices. Okay. And so so from here we have X is the inverse of C. So the conclusion is that C to B is the inverse of B to C. And it's very interesting. C to B, what is C to B? Actually, you can take B. You use the basis vectors, the vectors in the basis C. So that is U1, U2. I erased that. Anyway, so this UN, take the B coordinate. Alright? And this matrix is V1, C, V2, C, etc. Vn, C, etc. And then inverse. So you have this interesting result. Okay? So U1, U2, so remember, maybe I will put it here. B basis V1, V2 up to Vn, and C system U1, V2 up to Un. So we have two bases. So the transition matrix from C coordinate to B coordinate would be this one. Okay? And the transition matrix from B coordinate to C coordinate will be this one. Okay? And then they are invertible to each other. They are inverse of each other. Okay? And so this is generally true. You take arbitrary basis B and C. You will end up with this. Any questions? Okay, so I think I stop here and you will take a quiz.